We had technical problems in class on Friday, so very quickly I want to go through and rework that problem as a video for those who missed it or just needed a little extra assistance. Alright, so the question reads, liquid water flows at 1 millimeter per second over a solid that has been impregnated with formic acid at 320 Kelvin and 2 bar. The solid is a square 0.5 meter by 0.5 meter and is 2 centimeter thick. The mole fraction of formic acid in the solid initially is 0.10, and after 1 day of flow, what's the mole fraction of formic acid in the center of the solid after 1 day? Okay, a little repetitive there in the wording. So, I gave data. It is a little bit awkward to read, but this is actually a mu here, and this is actually a density here, and we want to know what the diffusivity is. Now, if you look in the book, first of all, this is liquid, so page 431 of the book has the data, and what we find is that at 298 Kelvin, the diffusivity is 1.52 times 10 to the minus 9th meters squared per second. Now, we have to remember that this is a liquid, okay? So the fact that it's a liquid changes the formula that I use. The formula is on the bottom of page 431, and for diffusivity, we see that pressure doesn't matter, but that temperature is to the first power in the numerator. So therefore, I can adjust the diffusivity by taking the old diffusivity and multiplying by the temperature divided by the old temperature to the first power, and there is no pressure correction. So therefore, in this particular case, I'm going to take 1.52 times 10 to the minus 9th meters squared per second. I'm going to multiply by 320 Kelvin and divide by 298 Kelvin. And I end up with 1.63 times 10 to the minus 9th meters squared per second. It asks for it in centimeters squared per second, so we're going to multiply by 10 to the 4th, 1.63 times 10 to the 5th meters squared per second. So the next part of the calculation asks us to find the Schmidt number. Now the Schmidt number is one of our dimensionless quantities, and it is mu over rho times the diffusivity. Mu is given above. Again, remember that the app that I'm using right now will not use Greek letters for me. So it's 8.71 times 10 to the minus 4th kilograms per meter per second. Density is 996 kilograms per cubic meter. And the diffusivity we just found. Now I want it to be in meters because I need the units to cancel. So 1.63 times 10 to the minus 9th meters squared per second. In this particular case, all the units cancel directly and we get 536. Next, it asks for the Reynolds number. The Reynolds number is going to be the velocity times whatever the characteristic length is, times the density divided by the viscosity. Tells me that the velocity is 1 millimeter per second. Again, I'm going to want everything to have units that cancel, so I'll switch it to meters per second. The length in this case is the length in the direction of flow. So I have this big square plate that's just a teeny bit thick, and the flow is going this direction. So in the direction of flow, the length is 0.5 meters. The density is 996 kilograms per cubic meter, and the viscosity is 8.71 times 10 to the minus 4th kilograms per meter per second. Again, the units all cancel. We get 571. So, is this laminar or turbulent? And if it is turbulent, where does the transition occur? So you have to know for your geometry what is the transition point. And for flow over a flat plate, the transition from laminar to turbulent is going to be, it's on the order of 30,000. Depends a little bit on different people's definitions, but it's on the order of 30,000. A Reynolds number of 571 is significantly less than that, so therefore this is laminar flow. Now that's important because of the next question. We want to know what Jsub D is. Now, for Jsub D, we need to know that, first of all, this is a liquid. It's not a gas. The Schmidt number on this is nowhere near 1. It's 536. And the Reynolds number is 571. And if we look in the book for flow over a flat plate that meets all of these conditions, okay, and let me write the flat plate part, okay, so it meets the geometry conditions, it meets the velocity condition, and it meets the fact that it's a liquid, okay. Equation 7.3-29 is the one that we want to use, and it says that JD equals 0.99 NRE to the negative 0.5. Now, be sure that you read all the fine print. Every time you go to a book or literature to use an equation, there's this tendency to say, oh, it's under this heading, so therefore any of these equations will work. I'll use this first one. Well, be sure to read the fine print around them because we've got to make sure everything is satisfied. Now, in this particular case, it is the best of the equations there, but frankly, this is for Reynolds numbers that are greater than 600. Okay, and I'm not greater than 600, I'm at 571, but it's really close, okay, and with rounding error, that's probably good enough. And so therefore, using this, Jsub D is 0.99 over the square root of 571, and I got 0.0414. So now, Ksub C prime, okay, equation 7.3-5 relates Jsub D to Ksub C. It says that Jsub D is Kc prime times the Schmidt number to the 2/3 power divided by V. And we, of course, are looking for Kc prime, so Kc prime is going to be Jsub D times V times the Schmidt number to the negative 2/3 power. Okay? And if you plug our numbers into this, again, being careful with the units, Jsub D has no units. The Schmidt number has no units. The units are going to come from the velocity. If I do it in meters per second, 0.001 meter per second, I end up with Kc prime as 6.28 times 10 to the minus 7th meter per second, or 6.28 times 10 to the, now this is just meter, not meter squared, 10 to the minus 5 centimeters per second. Okay, so next let's look at Ksub C. Now, Ksub C is not listed with the liquid values for K, but if you look in that table for flux, so table, let's see, it's 7.2-1, when they list the equations for flux, they do in fact have Kc and Kc prime used for liquids. But in the table below, they don't. So we're going to have to just kind of use the gas to get sort of an approach on how to do this. So for a gas, what we see is that Ksub C times the partial pressure of B sub log mean is Kc prime times the total pressure. Okay? If I divide everything through by the total pressure, I end up with K sub C is Kc prime over Y sub B log mean. So analogously, then for a liquid, K sub C ought to equal Kc prime over X sub Bm. Okay? And in fact, you could go through and do the derivations of the two and get the same result. I don't know why they didn't list it in the table. So now then, the next question is X sub Bm. What's going on there? Well, I have this surface. And the surface, initially I have X equal to 0.1. And out in the free fluid out here, I have X equal to 0. I'm going to assume that the liquid water is just pure. But I have this problem with A and B. So A is my formic acid, and B is the water. These are compositions of A. So out here, X for B is 1, and here X for B is 0.9. All right? So if I want to figure out then what X sub B log mean is, it's going to be the difference between these two X's, 1 minus 0.9, over the natural log of the ratio of those two. And that came out to be just right at 0.95. So Kc is my Kc prime, 6.28 times 10 to the minus fifth, divided by 0.95. And so we get 6.62 times 10 to the minus fifth centimeters per second. Now then, we're trying to find out about what happens over time. And we're going to be wanting to use the graphs that we borrow from heat transfer, okay? And so one of the quantities we need is going to be the diffusivity over Kc times L. So there's a couple of issues here. So DAB, we've calculated that earlier. That's 1.63 times 10 to the minus fifth centimeters squared per second. Okay, K sub C we just found to be 6.62 times 10 to the minus fifth centimeters per second. But what about L? L, I'm talking about a long, thin plate that is 2 centimeters thick. Okay, it's 2 centimeters thick. It's not very thick, but that's the direction that the diffusion is happening. It's going in that direction. And according to the tables, what you're supposed to use is the distance to the midpoint. Okay? So therefore, I want 1 centimeter is my L. This is not the same as the Reynolds number in this particular case. Okay? Because now I'm talking about a different direction. And so the direction here, L is 1 centimeter, and this quantity comes out to be roughly 0.25. If I'm going to take it to a graph, really 2 digits is fine. All right, so my next question is DABT over L squared. So I was given the time, so I'm going to be looking up that Fourier number, or its analog for mass transfer, which is DABT over L squared. DAB again is 1.63 times 10 to the minus 5 centimeters squared per second. L, same situation. I'm dealing with the diffusion going across the plate or out from the center of the plate. So it's that 1 centimeter depth. The time is 1 day. Okay, so 1 day is 24 hours. Again, my goal is to get all the units to cancel, so I need to get this to seconds. 1 hour is 3,600 seconds, and I end up with 1.4. Now we're ready to go to our graph. Now I see that I stretched the graph kind of funny on this. Okay, well, no big deal. I'm going to find the 2.5, or excuse me, 0.25 on these curves that come like this. Okay, and what I have is I have a 0.2 and a 0.3, and I'm just going to split the difference in there, and it's going to be somewhere right in there. Okay, so you're going to draw in your curve. Next, I'm going to find, in this case, I know this, and I'm looking for this. Okay, so I'm going to find the Fourier number of 1.4, and I'm going to find that in here. I'm going to go straight up and straight over this way. So I found 1.4, this is 0.25, and I'm going to read over here, and I found this to be 0.125. Okay, so what does that 0.125 mean? Okay, it is equal to, and it's got temperatures here, but remember we can use concentration, we can use mole fractions, we can use partial pressures, any measure of the driving force, that composition difference. So here it's y at the center minus y of the surroundings over y initial minus y of the surroundings. Now I'm looking for y at the center. Y of the surroundings is 0, and the initial y is 0.1. And so therefore y at the center after 1 day is 0.0125.